mathematics. And as you know, we are now running a workshop on purification of mathematical physics, and we asked organizers to select one of them or some of the other participants to give overview of what this is about for more general audience of physicists and mathematicians. And Piotr Sulkowski, who is one of the organizers, agreed to do that. So today he's going to talk about Knots-quivers correspondence.
Okay, thank you. That's a big privilege to speak here. And this is indeed the title of my talk, Knots-quivers correspondence. So this is a kind of excuse. I will try to present various things related to our workshop, whose title is Categorification in Mathematical Physics, but this also gives me a chance to present the work I have been doing in the past year with a few collaborators. So there are several reasons to give just this talk. Also, another reason is that in presenting this topic, I will have to summarize various ideas on the border of, let's say, physics and mathematics of knot theory, which have been developed maybe in the past 20 years or even a bit more. So maybe this is a good opportunity to do that. Yeah. So let me start. And the work, in fact, I like to present is, well, it has started in the collaboration with Piotr Sulkowski, who is also here, and Markus Reinecke and Marko Stosic. We wrote or presented the main idea in these two papers. And then several follow-up papers also appeared. Some of them were, well, there was a paper by Paul Wedrich and Marko Stosic. Paul is also here, so there are some people who are familiar with the topic. And, well, as the title indicates, it appears that there is some relation between two branches of mathematics, knot theory and quiver representation theory. We come across it by analyzing various ideas and inspiration coming from physics, but I will just start to explaining what the idea is. So when we talk about knots, we usually think of having one-dimensional curve embedded in R3. We can also think of knots embedded in other free manifolds, but for simplicity, let me just think of a knot in R3 or maybe S3. So this is a typical picture. This is so-called trefoil knot. And the idea of this correspondence is that for a knot, one can find some quiver. So quiver is a graph which consists of vertices and some arrows between them. And quivers appear, of course, in mathematics, in quiver representation theory, but also in physics, most often in the context of so-called quiver gauge theories. So let's say that one purpose of my talk is to explain in which sense this quiver corresponds to this particular knot. So this is an example of this correspondence I'm going to tell you about. And the idea is that to each knot you associate some quiver.
So why did you take the arrows off the loops?
Well, because loop points from one vertex to itself. So the arrow for me doesn't matter that much in this case.
This was symmetric and this is not. That's okay.
Well, I don't need to include orientation on arrows. Or at least I assume that for each vertex they are oriented in the same way. And so I associated this quiver to a knot in such a way that various invariants of knots turn out to be reproduced by invariants of quivers, or vice versa. And so let me make a small table. Where I will list some of these relations. So, well, some things, when you look at the quiver or not, some things are quite immediate. For example, number of arrows or loops We can just easily count them. And it turns out that they correspond to so-called homological degrees as well as the framing of a knot. I will explain what follows what I mean by this word, so don't worry if some of them are not immediately defined. Here you can see that this is something which we immediately see. This is a bit more involved, but there are various other invariants which are less.
Are you saying that the quiver depends upon not just the knot, but also a framing?
Yes.
It's a frame knot.
It's a frame knot. And somehow by varying the framing, I corresponds to varying either the number of arrows or number of loops. I will mention more details later. But there are, of course, more interesting invariants on both sides. In particular, there are not polynomials such as HOMFLY-PT polynomials or their colored versions. Which is something not, well, it is of course very nice, but not yet very elaborate. But it corresponds to something, let's say, more elaborate on the quiver side, namely to so-called motivic generating series. And this is quite an important relation because this enables me to discuss another type of invariants which are called Lmov Invariants. Lmov stands for Labastida-Marino-Ooguri-Vafa. So these are some invariants of knots whose existence was postulated by these physicists, and it seems that today they are not really firmly formulated mathematically. However, from various physical interpretations, I will mention them as well, it was conjectured that these invariants should be integer. It was checked in many cases that they indeed are, but the proof of this fact was missing. And through this relation to quivers, it turns out that one can prove that they are indeed integer, at least in some large families, because they turn out to be related to so-called motivic Donaldson-Thomas invariants, which are proven to be integer, at least in the cases which will be important for us. So through this relation, we can express this Lmov invariants through this DT invariants, as I will refer to them, which somehow proves integrality of these ones. And then there is a related family of invariants, so-called classical Lmov invariants and numerical DT invariants. So relation between these somehow follows already from relation of this kind of quantum invariants. And, well, there are other relations. So, for example, physicists for a long time have been trying to formulate what so-called algebras of BPS states are. And in particular such algebras are expected to exist also in cases related to knots. And it appears that through this relation, these algebras could be related to so-called cohomological whole algebras which are associated to quivers. And what is also somehow nice is that through this relation we can match various invariants to each other. But these are not only numerical invariants that are matched to each other. One could think just of the moduli space of quiver representations. Itself as some kind of invariant which is associated to a knot. So this is some geometric object, and having such a geometric object as an invariant of a knot is an example of some kind of categorification, one could say. Typically, in the context of knots, we use this word categorification in a slightly different context, but idea is somehow similar. And also, all these relations turn out to be related to the categorification and not homologies in such a sense as are typically considered. So this is also somehow nice that all these concepts get unified in that picture. And moreover, these relations also made contact with other branches of mathematics, in particular with number theory and combinatorics. So this is something I hope I will also manage to mention at the very end. So again, the main idea is that there is this relation, and somehow the aim of my talk, or at least one of the aims of my talk, is to tell you how to find that this particular quiver should correspond to this knot. And if you see that, you will have an idea how it should work for other knots as well. But before I do that, I should explain various of these concepts which I listed in this blackboard. And, well, to do that, I need a little time, and I need to review various concepts which have been developed, as I said, for last, like, maybe 25 years or so. So, well, I'm not sure if there are any questions, maybe just at this preliminary stage, or not.
A very general question, do you go from knots to quivers, or you go in both directions?
In a sense, I go from knots to quivers. At least this is the stage we are at now. So once you give me some knot and we have enough data for this knot, I am able to reproduce the quiver. And the opposite direction, I mean, it seems that there are more quivers than knots. So not every quiver corresponds to a knot.
Do you know what condition that quiver has to obey?
Well, first of all, you might already sense that the quivers we consider or that we find must be symmetric, which means that the number of arrows from one node to another node is the same as in the opposite direction. But this is not the full characteristic for sure. But it just happens that for this class of quivers, symmetric quivers, a lot mathematical information is known, and apparently precisely this information is what we need to discuss this invariance from the knot theory side.
The last line suggests that that's going into the knot.
Maybe. I mean, in a sense, it goes in both directions. Just at the moment, we know how to identify a quiver having a knot, and the other direction, well, it should also work. So one of our aims would be to be able to identify the quiver just from the picture, which we cannot do at this moment. We believe that this should be possible. We need to have more knot theory information, but at the end, we just get this quiver. So this is also one of the tasks. If anyone would be interested in this topic, well, we would need certainly some help trying to identify the quiver, just having a picture of a knot.
Is it a coincidence that the conical quiver is sitting in there?
That could be, at least in what we've been doing does not require having a conical quiver. And, well, you have just two vertices. Okay. All right, so let me review maybe some of the basics about knots and relations to quantum field theory and also string theory. So I need a little time to tell you probably most of all what the Lmov invariants are. Let me stress again that one of the main motivations for our work was to find some proof of the Lmov conjecture that these invariants are integer, which follows from this identification. So next maybe 10 minutes I will spend trying to tell you what these invariants are. But to tell you that I have to review more basic concepts. I'm not sure if everyone here works on knot theory, so I will start with something very basic like knot polynomials, or in particular Jones polynomial. So as many of you probably know, Jones polynomial is a polynomial in one variable, which I will call q, which gets assigned to a knot. And the way mathematicians or Jones assigns this polynomial is via so-called skein relation, which is some kind of recursion relation. Which tells you that if you have some picture of a knot like this one on the left, you have to focus on one crossing. You also introduce some orientation, and then you identify this crossing with either this one or this one, and then you replace it by opposite crossing or by such a resolution. In such a way, you get 3 knots, and then the statement has that the value of Jones polynomial for 3 knots, which you get in this way. These polynomials are related by this relation. And working recursively, you can reproduce how this polynomial looks like for various knots. For example, for trefoil knot in the notation I am using, it looks like this. If we choose the normalization that for the unknot, which is just unknotted loop, it would be normalized to unity. So this is how mathematicians introduce typically knot invariants, at least those classical polynomial knot invariants. Sorry?
Right-hand trefoil or left-hand trefoil?
So there are various types of polynomials, and one of them are more powerful or less powerful, and they either can detect this handedness or cannot. So Jones polynomial doesn't detect.
Which one is 3-1? Right or left?
Well, no, Jones polynomial doesn't detect.
No, 3-1, the note.
Oh, sorry.
The trefoil note may be positive or negative.
You drew a left-hand one, but I think this is the one for the right-hand one.
Well, probably you're right. But well, up to this handedness, what's important in my notation is that I use, if we are going into more technical details, that I use q here so that I get this q square, q6, q8. All right, so this is how Jones polynomial is introduced by skein relations. However, physicists often think of these knot polynomials by using relation to quantum field theory found by Witten in 89 and interpret them as expectation values of Wilson loops. So I will write a bit more general expression now, whose particular case is Jones polynomial, but this relation through quantum field theory enables to consider much more general families of knot polynomials. So what we consider is so-called Chern-Simons gauge theory, whose action is just the Chern-Simons action. It is known to be topological theory, and I will just write in a moment. The claim of Witten is that if we consider the following path integral with inserted trace in certain representation of the exponent of this gauge field integrated along the loop, which is a given knot we would like to consider K. Then we get invariant, in this case, of this knot. And it should be normalized also by the partition function of the manifold itself, I mean of the path integral without any insertion. This can be defined on any manifold, but as I said, I will be considering mainly R3 or S3. And then the relation between parameters is such that Q is 2 pi exponent of 2 pi I divided by K. I could be more general, but I will assume that I am considering SUN gauge theory here. So here is this N. And then A is Q to power N. And with such an identification of parameters, this PR turns out to be reproduced colored HOMFLY-PT polynomial. And if n is taken to be 2 or a is taken to be q squared, then we get Jones polynomial. So that's in case you have not played with that. For trefoil knot, in the fundamental representation, this Humphrey polynomial looks like this. And, well, it has, of course, a lot of nice properties. And among these properties are very important one, which have to do with certain integralities. And I will be interested in two types of those integralities. One is immediately related to this field of knot homologies, which is also a topic of our workshop. And another one is related to integrality of these Lmov invariants. But at the end, they will turn out to be somehow interrelated. So let me just briefly say that the first integrality has to do just with coefficients of these polynomials. And that was Mikhail Kovanov, who is here, who proved why, well, at least first in the case of Jones polynomial, why the coefficients of Jones polynomial need to be invariant. And the reason is that they arise as dimensions of certain homological spaces. And more general, idea is that various other types of polynomials can also be realized in the same way. Namely, they are expected to be Euler characteristic of certain homological theories. So one of the ambitious goals in this field is to define such homologies which would reproduce colored HOMFLY-PT polynomial. And, well, this is not quite achieved, at least to my knowledge at this moment. However, what can be done, at least in this case of colored HOMFLY polynomial, is identification of Poincaré polynomials, which are like an intermediate step between just ordinary polynomials and these homological spaces. So these Poincare polynomials are also known under the name of super polynomials, and they have been introduced by Jake Rasmussen and Sergei Gukhov, who are also here, and also Dunfield. And even though in various cases we are not able to identify these homological theories themselves, there are postulated certain conditions which enable us to find these polynomials, which depend on this additional t. So I will just write the example, because this will be immediately related to this relation to quivers. For trefoil, this super polynomial takes the following form, and just to give you a glimpse of what we are aiming at, namely this first line, those number of loops which are in this picture are related to the powers of t in the super polynomials. Namely, these powers are 0, 2, and 3, and this will turn out to be the reason why we have this number of loops in the quiver. So in this sense, these quivers also know something about those knot homologies. And as I said, this is one type of integrality, but there is also another one which is maybe a bit more intricate. And this other one is related to this work of Labastida-Marino-Ooguri-Vafa, and it has to do with the realization of knots in the context of topological string theory. So this idea is related also to one other work by Witten from 1993, where he showed that Chern-Simons theory can be realized as some particular type of topological string theory. And the upshot of this work is that if one considers Chern-Simons theory on some free manifold M, then this is like an effective theory which describes some kind of topological string theory on the manifold T star M, cotangent bundle to M. And later on, this picture was generalized to situation where in this M we also introduce knots. And Ooguri and Vafa found a way in which information about knot invariants is furthermore captured by spectrum of certain BPS states when this topological string theory is furthermore embedded in the full superstring theory. So the way that this string theory, this topological string theory knows about knot is such that to realize in the first step just Chern-Simons theory in the context of knot theory, we have to consider a system of so-called branes which are wrapping this manifold M. And then we need to consider another set of Lagrangian branes in this system which are intersecting this M along a knot. And one can then compute the physical partition function for this system, which turns out to capture at the same time the whole set of knot invariants. And then the statement of Ooguri and Vafa is that one can rewrite this function in such a way that it captures certain integralities which count the number of M2 and M5 branes. So well, I will not present details of this derivation, but the bottom line is that this partition function of that physical system turns out to take the following form. So from this set of branes which are wrapping just M3, and there is this knot realized by the intersection with the other set of knots, one gets the values of colored HOMFLY polynomials. And because of the presence of this other set of branes, we get a generating function which just assembles all these colored HOMFLY polynomials all together. The sum is over all possible representations. And this V can be interpreted just as a source, some fixed set of generating parameters. And then in these works that I mentioned, it is at least postulated that this generating function can be rewritten in the following form. In terms of certain functions fr which have a very specific structure, namely, well, let me write it here. Namely, these functions capture these multiplicities of M2 and M5 branes, which I mentioned. Which are those ends. And then for a long time it has been a puzzle how to prove that these ends are integer. So from physical interpretation it follows that they should be integer, but it is not completely obvious. This conjecture has been tested in many examples, but they were restricted mainly to the cases where these representations are represented by Young diagrams with just several boxes, because it is also quite hard to find explicitly the form of these colored HOMFLY polynomials for larger representations. And then there are also some physical interpretations of these numbers and also of these homological spaces, as I mentioned. They are identified also by Sergey, by Schwartz and Vafa with Hilbert spaces of these BPS states of branes that I mentioned. But, well, I would say this is more conceptual interpretation and does not give, like, mathematical proof that this should indeed be integer.
Yeah. Still going to speak about quivers?
Yeah. So this is more or less, thank you. This is more or less like half of my time, and I just very briefly reviewed what are the relations between QFT and strings and knots. But I did it because I wanted to. Well, I did it to introduce the Lmov Invariants. Yeah. So now, indeed, this is the point when I was going to tell you more about quivers, but you will see all this, what I said now will be necessary. Okay, so mostly what I am interested in regarding quivers are moduli spaces of quiver representations. I will just say a few words about that, but just to make sure, are there any questions to this previous part of the talk? It seems there are not. Okay. Okay, so as I said, quiver is thus a graph which consists of certain vertices, some arrows between them, and typically one assigns some numbers to the vertices. So in physics, quivers appear, as I said, in the context of gauge theory. This is one place where they appear, and then these numbers denote the ranks of the gauge groups that physicists consider. In mathematics, in quiver representation theory, one considers representations of quivers, which means that each of these nodes represents certain vector space of dimension given by this number, and then the arrows represent possible linear maps between these spaces. So all these numbers d are assembled into so-called dimension vector. And one issue which is important for me is that I will not fix these to take some particular values, but I will consider all possible sets of these at once. I mean, there is, of course, the restriction that they have to be non-negative integers. So moduli space of quiver representations for a fixed dimension vector is a set of all such maps. Let me just say that denote a map from vertex I to vertex j associated to some arrow A by BA ij. And let me assume that also all these vector spaces are just complex vector spaces. Of course, one can be more general, but I don't need that. So moduli space of moduli space of quiver representations is this set, possible with some other conditions. One can also consider certain potential associated to the quiver, which in fact, in my case, will not play any role. And one can also consider certain stability conditions, but I will also not consider this. One important thing is that one has to model this out by GLDI, the product of GLDI groups. So mathematicians would like to identify the spaces, or at least find some characteristics of those. And more or less, this is what the T invariants are. So I will also not introduce very formal definitions, but just let me say that, roughly speaking, these T invariants are dimensions of various homology groups of those moduli spaces. And the question is how to find them. And in general, it is hard, but there is a theorem which tells you how they can be identified for symmetric quivers. So namely, what one has to do is to consider the following generating function. This is this, I already raised that. This is this motivic generating function that I mentioned in the very beginning, which has some universal form, and it depends on the data of the quiver. And the sum is over all these dimension vectors. So this is Q to some power which is quadratic in the IDJ, and this Cij is these are entries of a matrix which tell you how many arrows we have between vertex I and vertex J. And then in the denominator, I have a bunch of Q Poch-hammers, and then a bunch of these generating parameters xi to xn.
Okay, quiver is symmetric. It's saying that Cij is Cji.
Yes, Cij is equal to Cji. And then the statement is that if one finds a product decomposition of this expression into so-called quantum dilogarithms, then this product decomposition has the following form. So in particular, the product over K is something that gives us this structure of quantum dilogarithms. So for each fixed set of these and fixed J, the product over all K gives one quantum dilogarithm. And then these powers which appear here are those motivic DT invariants associated to a given symmetric quiver. So this identification has been found by Kontsevich and Soibelman. And they also conjectured that these numbers should be integer, which was then proven by Efimov. Okay. So all these omegas, D, J, in fact, it is proven that they are positive or non-negative integers.
What is in the denominator?
This binomial, okay, let me write it, what it is. So in general, x, q, k is a product I from 0 to k minus 1, 1 minus x, q to power I. Okay, so apparently this is all the information from quiver representation which I would need, because now this structure turns out to be very similar to this structure. You might not see that immediately yet, but it is useful, and this is what I will do, in fact. It is useful to focus from this perspective on representations which are symmetric powers of the fundamental representation. So I will denote them like that.
If you instead use skew-symmetric, would it be the same given the symmetry between columns and rows?
I could, at least if I consider, I mean,
With a slight different variable.
yeah, I could, at least in the context of HOMFLY-PT.
So it doesn't matter for you.
But it can be generalized to super polynomials, whatever I'm saying, then this is maybe less trivial to identify colored superpolynomials, but I could. The short answer is that I could. Okay, so if I consider symmetric ones, then this trace of whatever is equal either to well, maybe the way to say that is the way to achieve this is to consider the source, which is here. In principle, that could be any matrix, is to take it just to be a 1-by-1 matrix. And then it follows that a trace in any representation of that is simply either x to power r in case this representation is the symmetric representation, or this is 0 in all other cases. And then if one considers just such a one-dimensional source, then this partition function reduces to the following one, which I can write now in the product form, because essentially of this 1 over n, and if you play a bit, you see that you get something like exponent of the expansion of the logarithm. So in particular, in this case, you see that this product structure of this Ooguri-Vafa partition function is very similar to the product structure arising from this Kontsevich-Seiberman formula for the Motivik-Donaldson-Tonas generating series. With some, well, small differences. Of course, here we had more generating parameters, so one has to specify them somehow to identify them with the single parameter here. But the crucial point is that these Ooguri-Vafa invariants which appeared in this exponent appear on a similar footing as those DT invariants in this generating series. So if you play a bit more with this expression, you come to the conclusion, which is our main conjecture, or let me say a claim, which is the statement that generating functions of colored HOMFLY-PT polynomials colored, well, let me say symmetrically colored. Can be written in the form of the quiver generating function for some quiver with the following specialization of those parameters xi. So each of the xi's has one term which is just x, which appears in the Ooguri-Vafa generating function. And then this is multiplied by aq and minus 1 to the powers, which are degrees of the generators of the HOMFLY homology. So this set of ai, qi, and ti or more pragmatically, these are simply the powers of monomials which appear in the uncolored superpolynomial. So just to have an example, let me recall again what was the superpolynomial for the trefoil knot. So those powers which appear here are correspondingly AI, QI, and TI, and they just enter into this specialization.
So what is C?
Yeah, and C is the matrix which identifies or captures the information about a given quiver. So C is a matrix with entries C, I, J, which tell you.
But this is a question about HOMFLY polynomials for the knot. Yeah. So what's the relation?
Yeah. So okay. So this is the issue that we claim that maybe I can be a bit more explicit. I think I can raise this. So for a moment, you might even forget about the quiver. And the expression I wrote is the following one. So our claim is this generating function of HOMFLY-PT polynomials takes the following form. We have the sum over all these non-negative sets of integer. There is x to this power. And then there is q in some power which is quadratic in those d's. There is a bunch of q binomials. And there is a set of terms which are q's, a and -1, just in linear powers in these. So we just claim that generating function of this HOMFLY-PT polynomials can be written in this form. And once you are able to do that, you can identify what this Cij must be. And then you see what is...
Where are knots? Is it about knots of some invariant HOMFLY polynomial of some knot?
Yeah, that is what I mean. Well, so conjecture is general. And I will tell you in a moment for which knots we can do that.
General conjecture, there should be initial data.
Yeah, I will tell you.
The initial data, I guess, should be knots, right?
Yeah. So here.
Conjecture is that it holds for any knot.
Yeah, conjecture calls that it's for any knot.
But anyway, there should be a variable introduced.
For every knot, there exists a quiver, or
Yes. Well, I tell you that for every knot, if you take generating function of this colored HOMFLY-PT polynomial, you can rewrite it in this way. And then from this expression, you can read off what is this matrix Cij. And on the other hand, you know that this expression has the same form as motivic generating function for some quiver, with the Cij being entries of the quiver, of the matrix which defines the quiver. So for example, I didn't write, but it is, I could, but I don't have that much time. But there is known general expression for colored HOMFLY polynomials for the unknot. So once you take that expression and play with that a bit, you may bring it to the following form, and then you see what the Cij should be. You see that it is of the following form, and essentially this is the matrix which tells you what is the structure of this quiver.
So I just want to understand what you're doing. So you are computing the quiver using these formulas. You're sort of actually constructing the quiver using these formulas. So you find the Cij using these formulas and then write down the quiver.
Yeah, I somehow identify this quiver. Yeah. I mean, I'm at this moment, I need to know this colored HOMFLY polynomial to be able to identify what the quiver is. So as I said in the beginning, it would be nicer to identify it, let's say, just from the picture, but we cannot do that now. But
maybe you read off as just Cij and the multiplicity of Dj.
No, I sum over all those d's. So, but this has very particular power. So this is q. Here are just quadratic terms. So from these quadratic terms, I identify Cij. And moreover, I see what are powers of these linear terms, from which I can see what this qi, ti, ai are. And I see that they agree with these homological degrees. And in particular, these TIs, I'm not sure if I said that, but these TIs are equal to diagonal terms on the matrix. So those essentially number of loops. Okay, and you are asking what is, how general it is.
How do you fix the value of n?
Value of what? M? Well, I can fix that because the structure of the summation is somehow quite constraining.
Is it possible to read off M from the knot more explicitly? It's not like
Yes, M is the number, just from what I said, that this AIQI, I agree with those homological degrees. It means that M is the number of HOMFLY-PT generators, namely the number of terms in the superpolynomial, uncolored superpolynomial. So, one outcome of that is that you see that if you know this matrix and you know this finite set of integers AIQI, TI, you know all colored HOMFLY polynomials for a given knot. And this question has already been asked. How do we know that this is true? So we don't have general proof, but we have, let's say, partial proofs. Well, what statement? The statement is that if you...
You're going to prove some statement, right?
Well, I'm not going to show you the proof.
Okay.
But the statement is here.
Statement.
Well, I don't...
So
This is the statement, that if you take colored HOMFLY polynomial of a given knot...
How knot comes in? How does it come? So you had trefoil. What to do with this trefoil afterwards?
All right. The statement is that for any knot, if you write this generating series of HOMFLY polynomial for the knot, it can be rewritten in such a form. That's the statement.
Generating series.
So, Alec, you colored trefoil with rows. Each row gives you a polynomial. You add them. You write them. This generating function has a very special form, which also comes from quivers. They can identify the quiver looking at that.
Good scheme.
Well, so... as it has been already said, it's conjecture that it holds in general, but we have proven that in various special cases. So first of all, for all knots up to sinks crossings, and then you see, well, if you start playing with that, you see that it's quite non-trivial. So for like 6-2 and 6-3 knots, these quivers have size like 11 and 13. So if you try to play a bit, you already see that this is not an obvious thing. With various families of torus knots, not all torus knots, but at the moment we have the proof for the family of 2, P and 3, P torus knots. And then there is a paper I mentioned in the beginning by Paul Bedrich, who may be somewhere here, and Marko Stosic, who proved this for all rational knots. So this is also quite a big family. Well, and also some other examples like twist knots. So if you call it initial data from which the conjecture started, let's say that here it is.
So there's a framing that's involved, and what changes?
Yes.
What happens in practice to the...
Yeah. So let me now tell you some comments. Indeed, framing is one of them. So if you change a framing by 1, then you change quivers in a very simple way. or a change in framing by F means that we have to replace a quiver represented by matrix C by quiver represented by matrix which has F's everywhere, which means that we add F loops and F arrows between each vertex. So, well, so we don't have properly defined quiver at that case, but what we can always do, we can use this freedom to shift it in such a way that it is positive. But the structure of generating function is still there. What is also quite non-trivial is that we can predict the forms of colored HOMFLY polynomials in various cases in which they have not been known before. Because, well, we can always find several colored HOMFLY-PT polynomials using formulas like Rousseau-Jones or so, but to use them one has to work thus, case by case. But once we have those first set of HOMFLY polynomials, we can see from which quiver they must come, namely this formula that well, this formula is quite restricting, and finding sufficiently many but finite number of this colored HOMFLY, we can find general formula. And as I said in the beginning, our main motivation for that was the proof of this Lmov conjecture, at least for symmetric representations, and it just follows from this construction. Namely, at least if we have a knot and we are able to find the corresponding quiver, then we immediately know how to express the Lmov invariants through Donaldson-Thomas invariants, which have been proven to be integer. So we hope that this is quite an interesting result. And also this relation gives hints to various generalizations. For example, on this quiver side, we have in this generating function dependence on this whole set of generating parameters, which indicates that also not polynomials could be refined in the corresponding way, which is not, well, it seems it has not been considered before. And on the other hand, we know that this not polynomials are labeled by representations, which can be more general than just symmetric. So it suggests that on the quiver side, one could also consider more general classes of invariants than just those which, well, in this relation correspond to symmetric ones. And, well, I think this is the moment where I could stop.
So you're reading a number of the vertices from the usual HOMFLY, right? So the number of the vertices, or you see it from the usual.
No, I need to take super polynomial because
Super polynomial, yeah, sorry.
if that would be negative signs, some things would cancel.
C matrix, you have to know all of the colored ones?
No, just uncolored one.
And from that you also can get your matrix C?
No, from this I can just see, as I mentioned, the number of loops, but not the numbers of arrows.
But number of arrows, you need to know symmetric ones,
For number of arrows, well, I don't have immediate geometric interpretation, or I mean, I can see them by some rewriting of this formula, but this is not immediate to tell you where they come from. So they come from the structure of
So basically, you have to kind of guess.
Well, compute, so to say. So I get the result from the computation, but I don't see it simply from super polynomial.
So what is the not-quiver correspondence as well? To a knot,
Well, I claim that to a knot I assign a quiver in such a way that various types of knot invariants are reproduced by data of moduli space of representation of this quiver.
What quiver do you assign this one?
To a trefoil, I assign this one.
One.
1.
Not a family, but this one.
Just this one.
But if
And
you change the framing, you do change the number.
okay, if I have a frame node, then I can consider a family of those quivers which differ by that change.
So for each framing, one.
Yeah, but so if you twist by -1, you're going to disconnect it. It'll have like missing.
Yes, yeah, it might happen so.
What are the D's?
What is, sorry, what?
D.
D?
Sum over D's.
Sum over these were those dimension vectors. So on the, in fact, on the, you may say that this R which appears here is a sum of all these, but those D's themselves are dimension vectors from the quiver side.
So this way you reproduce only the row diagram.
Yes.
So can you interpret this that you have those Lagrangian submanifolds in the conifold, and you look for elementary disks, D2s, which give you the generators of homology, and then you simply put the stacks of those D2s, the multiplicity is reflecting the numbers D, and when those disks intersect, this gives you arrows. So would that be?
This, I'm not sure. I didn't say that. So in fact, also one motivation for us to find this quiver is that also from physics grounds, we would expect that there should be some effective quiver quantum mechanics describing this system.
Maybe I can comment that with Tobias Ekholm and Piotr Sulkowski, we were doing something of this flavor. I think that your picture seems to be right.
So because a stack of disks would give you, I think, a column actually, but
So HOMFLY polynomial has nice specialization when you get SLN invariants or SUN. So what happens to the quiver side of this specialization for the DT invariants? Do they have some special meaning for this specialization?
I'm not sure. I mean, you're asking whether this quiver invariants also come in different kind of
Whether you can
flavors.
in this specialization, whether the quiver invariants can be described simpler than the general.
I'm not aware of that. To be
The correspondence, anyway, is it possible to formulate it geometrically?
In which sense?
In the sense that you are given with a picture and you produce a picture, there is some similarity between the
Yeah, so I stress that we cannot do that.
The picture on the left-hand side is sort of symmetric.
That's
and this one is not.
There is some similarity, but this is accidental, I would say, in this case. And I said already in the beginning that we don't have such a geometric picture. You would like to take a knot or this diagram, manipulate it somehow, and get this quiver. Yeah. We cannot do that at this moment. But one reason of me to give this talk was to also encourage some people in the audience that maybe some would be able to do it.
I suggest to stop here, and we have 2 days before Piotr leaves to come up with geometry.